Welcome to Brain Vision.
Hello everyone, this is the solution to problem 23 of chapter 24 of college physics. In the first part of this question, we are given a range of wavelengths that the human eye can register and see, and we're asked to find the corresponding frequencies for these wavelengths. So to find out what the frequencies are, we can use this relation between the speed of light and its wavelength and its frequency to rearrange this formula for f to get that f is lambda over c. And now if, the other way around. So we have c over lambda. C over lambda is the right formula for the frequency. And so putting in the values of 3 times 10 to the 8 meters per second and lambda 1 and lambda 2, we find that f1 is equal to 4.28 times 10 to the 14 hertz, while the frequency of the longer wavelength wave is 7.5 times 10 to the 14 hertz. All right, so in terms of frequencies, the range of visible light in air is frequencies from 4.28 times 10 to the 14 hertz to 7.5 times 10 to the 14 hertz. For the second part, we're asked to find how the frequencies and the wavelengths of these waves change if we are underwater. And we're told that the refractive index of water is 1.33, which means that the velocity of light in water is going to be its velocity in air or vacuum divided by this number 1.33. Now, one thing that we do know is that the frequency of the waves is not going to change. And the reason behind this is that the energy of a photon that carries this electromagnetic wave is going to be given by h times f. And so f is a fundamental property for an electromagnetic wave that doesn't really change. But the wavelength is not going to stay the same. And because the velocity changes, the wavelength is also going to change. So if I just substitute in the speed of light in vacuum here, then we're going to get that this velocity is equal to lambda times f over n, right? And since we know that the frequency doesn't change, we know that the velocity is going to be given by lambda over n times the same frequency. So then all we really have to do to find the wavelengths of these electromagnetic waves that had a wavelength of 400 nanometers and 700 nanometers respectively in air, we just have to divide these values by n. And so we get that lambda 1 is actually equal to 300 nanometers. And lambda 2, I guess I should call this lambda 2 and lambda 1 prime for W for their values in the water. And so for the 700 nanometer wave, we get that the wavelength in water is 526 nanometers. And so again, just to recap, I got these numbers by dividing the wavelength by the refractive index. So that is our solution.